Okay, so welcome everybody to our routing, switching essentials class and certain training class. We're going to talk today about dynamic routing. We had an entire chapter on static routing and discussed what static routing was for both IPv4 and IPv6. We configured it and we looked at some different items. I've already talked a little bit about some concepts that go along with what we have here, and we talked about two concepts that I'm going to put back up here: administrative distance and metric. And so defining these two, we talked about a metric was how you find the best route within a single routing protocol, or routing, not just say just protocol, but routing source. We'll say source. Administrative distance is how to find the best route between protocols. Okay, so it's kind of a trustworthiness of the source of the route. We talked a little bit about the AD. What is the AD for a static route? Y'all remember that?
I was me. It's 1.
Okay. What is the? Okay, so this is a static route. What is the AD for RIP?
120.
That's 120. That's RIP. How about EIGRP?
Internal. 90.
90. Okay. Now I will tell you this is internal.
Yeah.
Internal EIGRP, just so in case somebody says no, it's not. Well, that's internal. Now what about OSPF?
110.
110. Very good. Now these are all. If we had a route to the same network that was from static and from OSPF, the static route goes in the route table because it is considered more trustworthy. This, in the Cisco iOS, Cisco considers an internal EIGRP route to be more trustworthy than an OSPF route. Okay. But now, if we had the multiple routes to the same destination network via OSPF, we would need to use the OSPF metric to determine which one of those was the best OSPF route. And in OSPF, it uses an item called cost. I used an example way back in chapter 1, I believe it was, maybe 1 or 2, about how we determine where we go eat lunch. Today we ate at a Mexican restaurant because I really wanted a California burrito. You know, it had nothing. My metric today was the type of food. And so we look at different metrics within a routing protocol, just like we look at different metrics for where we go eat lunch. And each routing protocol has a different metric. The one we're going to talk about today, which is RIP, and it is an older protocol. We're going to have a V1 and V2. Okay, its metric is hop count, and it means hop count is every single router you go through is one hop. And so RIP looks at routes and says the shortest hop count has to be the best route, which is not necessarily always true as we've seen in the past. Here we can kind of see some of the different routing protocols when they came about. EGP, which you really haven't heard much about at all. This is a precursor to BGP. It's an older, real old protocol we don't use anymore. There's IGRP came around. You know, there's RIP v1. So you actually see the IGRP was around, right, and really not just a little bit before RIP v1, but open source path first. All the way up to now, we've got EIGRP for IPv6 and OSPF version 3. Routing protocols that are all different types. Now, we talked a little bit already about distance vector versus link state routing protocols, but I want to do a little bit more on those just so you got a little more background. So let's talk about distance vector. Okay, these protocols are sometimes called routing by rumor, because in the distance vector world, typically you look at, you're talking only to directly connected neighbors, and those neighbors tell you their distances or their distance vector to certain other networks. RIP v1, RIP v2, they're all distance vector routing protocols. Does anybody remember the difference between interior gateway? I think I've already gone over this with you. The difference between interior gateway protocol and exterior gateway protocols.
Interior gateway routing protocols, they route within an autonomous system that's designated by the ISP or INA, and the exterior gateway routing protocol routes between two different autonomous systems.
That is correct. So an interior gateway system, we talked about autonomous systems. We talked about that in chapter 1, I believe, it's autonomous systems. And that is a group of routers under the control of a single entity. Man, my throat's coming out now. Under control of a single administration, usually running a single IGP, interior gateway protocol. And then EGP, and the only one we have today is BGP. BGP runs between autonomous systems. So that's why they're listed as distance vector and, interior gateway protocols and exterior gateway protocols. Underneath that are our two subtypes, which are distance vector versus link state. Typically, distance vector had it sent their entire route table at a predetermined interval. Okay, so they did not do what was called periodic. They did periodic updates instead of triggered updates. So this is a periodic update. So like RIP, every 30 seconds, regardless of whether or not there's been a change to the route table, it sends its entire route table to its neighbor. Now, EIGRP is a little different. It used to be years ago, we called EIGRP a hybrid protocol. We don't do that anymore. We call it is a true distance vector protocol, but it's a distance vector protocol with some link state features. Now, what do link state do? Okay, link state, routers have an entire view of the network. Okay, so they understand the entire topology. They share link state information with the entire network. Okay, they typically use triggered updates. So in other words, once they initially flood out all their link state information, and everybody agrees upon the topology, and we get into a state where the network is stable, the only time there are going to be really updates that go out, true link state updates, is if a link goes up or down. So there's not this every 30 seconds sending your entire route table out. Typically, we consider link state routing protocols to be better protocols. Again, when you look at the administrative distance for EIGRP versus OSPF, Cisco has decided EIGRP is better. For years and years and years, EIGRP was a Cisco proprietary protocol. It has now been released as I would say a semi-open standard. I wouldn't call it an open standard, simply because it is out there as, quote, an open standard, but almost nobody has actually implemented it in their devices because they still consider it to be a Cisco proprietary protocol. Questions about these two? I know there's more in here as we go through. Keisha?
No, I don't have any questions.
Okay. So why use dynamic routing? Well, one of the big reasons is because they do dynamically share their information with one another. The advantages of that is obviously if a route goes down, you can update your neighbors without having to put in a static route. The other thing is, especially in large networks, it's very difficult to do static routes that will work. But each one of these has some type of data structure, in other words, where it stores the routing information. We're going to learn that RIP is very simple. RIP basically finds the best route and puts it in the route table. That's all it does. Once we get into EIGRP and OSPF, we'll learn about neighbor tables, we'll learn about topology tables, we'll learn about the different data structures that are used to support the routing protocol. There are also different messages, routing protocol messages. With RIP, it's just updates. Okay, they send out their entire route table at 30-second intervals. And you're actually going to learn that RIP does do triggered updates because although they're not required by distance vector routing protocols, they also were not limited or were not specified as not being available. So when Cisco did RIP, they actually put in a triggered update where you make a change, it will send out the table. So don't get confused by that when you're doing labs because it is a little confusing at times. But there are messages that go back and forth. For instance, again, with RIP, it's simple. It's just your updates. with OSPF and EIGRP, you've got neighbor hello messages, so you establish neighbors. You've also got with OSPF all types of link state advertisements, different types of link state protocols, and link state packets that you send out. Then there's the algorithm, and that's how you find the best route. So in other words, the algorithm is what's used to find for the metric. RIP, very simple. You got lowest hop count, you're the best route. In OSPF, if it's the lowest cost based on the speed of the interfaces, then that's your best route. EIGRP is based upon bandwidth plus the sum of the delays to the networks. So each of those routing protocols has their own way of doing the metric. Now, I'm not going to spend a lot of time on static routing because we know the advantages are it is secure, it's easy for a small network. It's always the same route. There's not much CPU or RAM or bandwidth used on the network. So that's the good things about routing, static routing. The disadvantage is, again, they do not easily recover from topology changes. Large networks, it's very hard to do static routes. And if you need to reroute traffic, unless you've used a floating static route, which we did learn about, which I like, then manual intervention is required to reroute traffic. You remember what a floating static route was, either one of you?
Mm-hmm.
What was it, Keith?
Okay, I don't want to be the only person. It's a backup. It's a backup route to any route in the routing table. It could be a backup to a dynamic route.
Well, not a dynamic route. It's usually a backup. It's a floating static, so it's usually a backup to a primary static route.
Right.
Okay. And to do it, all we do is what? Put at the end of the static route?
AD value.
Some AD value above 1.
Mm-hmm.
So 200, whatever. Just don't do 255 because that's unreachable.
Okay.
All right. So dynamic routing. What are some advantages? Well, they're suitable for all topologies, big or small. They automatically adapt to reroute traffic. They can be more complex depending upon the protocol and the size of the network. And also, we're going to learn about, we won't learn about it in this class, but as we move forward into scaling and connecting, you're going to learn about multi-area OSPF, and you're going to learn about how to, a little bit of redistribution of EIGRP and other protocols and those types of things. But they can be more complex. They are less secure because by default, they don't have authentication turned on. So to make them secure, you have to turn on authentication. Route depends on the current topology. Again, you're not absolutely certain where the packets are going. And they do require additional CPU, RAM, and link bandwidth because you're going to have to send out those route table updates or those neighbor hellos or whatever. And then you're going to have to hold those data structures we talked about a couple slides ago. You have to hold those data structures in RAM, and you also have to build those data structures using your CPU power. So they do take additional CPU, RAM, and link bandwidth. Now, here's the beauty, though. We're going to talk about RIP. Routing Information Protocol is ridiculously simple, okay? I'm also going to tell you about something that's very important, and that is this. Do not forget this. On 99.99% of the routing protocols in the world today, the only thing you're ever going to advertise are the routes that you are directly connected to. So when you look at R1, and R1 is configured to set up for RIP, you're going to have two network statements on RIP. You're going to have a statement for the 1-0 network, and you're going to have a statement for the 2-0 network. And that's it. You don't put these other networks in there because if you're not connected to it, if you don't have a path to it, you cannot advertise it with RIP. That's a key point. All right. So on R2, you would have 2 routes, or 3 routes, and then R3 would have 1, R2, excuse me. Now, how easy is it to do RIP? You put in router RIP. So router RIP turns it on. Now this means you're going to be running version 1 unless you put in the version 2 command. okay? But that's it, and that gets us into a sub-configuration mode called config-router. Now, if you want to disable it, you just do no router rip. Then we're going to advertise our networks, and like I said, you're going to advertise the networks you're connected to. Now, it's pretty simple. I want to show you something. I'm going to actually go in to NetLabs and pop open. Let me do this here. I'm going to bump up my font size and play around. I should have done all this before, but I had another, my other class was using this. All right, so I'm going to, the route, the network I'm working on is this one, okay? So I'm going to go in here, and I'm on R1, and I'm going to go config T. First thing I'm going to do is line con 0, logging synchronous, so I don't have that junk going across my screen. And I can't type. All right, I'm going to type exit, and I'm going to host R1. Int GI01. I'm going to make up my own IP addresses. IP add 192.168.12.1, 255.255.255.0. And I'm going to do a, let's go, I got to go to S000. And I'm going to do IP add 10.0.0.1, 255.255.255.252. Since this is a serial interface, I'll do a clock rate on it, and it is the DCEN, so clock rate, just do 64,000 for right now. By the way, what if I didn't have this little diagram telling me where the clock rate was? What can I put on here to find out? Anybody know?
Is it show controllers?
Yep. Do show controllers S000, and it will actually tell you what's connected. Look at that. It tells me there's a DCV35 connected right there. Good command to keep in your back pocket just in case you don't know. Now I'm going to do a no shut. And I'm going to do router rip. And I'm going to go ahead and do version 2, folks, so that we don't have to worry about auto summarization. We'll talk more about that in a second. I'm going to do network, and I've got the 192.168.12.0. And I'm going to do network. All we got to do is the major class pull network, even though we're doing version 2, because it will pull the subnet mask off of the interface. And this one I'm going to leave the same just because I know it's a little small, but just to give it for speed's sake, I'm not going to change the colors on it. All right. And then I'm going to do host R2, line con 0. Man. Logging synchronous. And then I'm going to do router rip. Router rip. I'm going to do V2, and let's see, network 10.0.0.0, and then I need to go to int S000 IP add, and all I did on this, folks, is I just did the first subnet on the big 10 network with a /30. So, and then no shut. And then now do shows CDP neighbors, and we should see if we should get a neighbor here. Yep, so we can see R1, so we know we got a layer 2 connectivity. So let's now do let's just do a control Z. Let's do a show IP protocols. I'm gonna make these a little bigger, so we'll make the font size slightly bigger. Okay. And we see here that we are running RIP, and we're advertising the 10 network. Okay. Now, if I do a show IP route, why am I not getting anything? So I'll do a show, let's do a show IP protocol here. Okay, so I'm doing RIP and I'm advertising the 10 network and the 192.168.12 network. Why is that 192.168.12 network not being advertised over the R2?
The 192.168.12 dot what? It doesn't have anything to do with network summarization. Did you do, we're
Nope.
trying to figure out what you got going on.
Look at this.
You haven't mentioned, you didn't do a no shut on your gigabit. No, not that.
Right. Remember what I told you? I did this on purpose. I told you that the router will not advertise a network that it cannot get to. And so if I do a show IP route right now on R1, you can see I cannot get to the 192.168.12 network. So even though I am telling it inside, even though I'm telling it inside of RIP to advertise that network, it is not advertising it because it does not actually know how to get there. So now if I do a config T and go to int GI01 and do a no shut, watch what happens. Okay, now, well, here in a minute when it comes up. Now I've got a route to 12. Now if I go back over to R2, watch this. Now I've got a RIP route. Okay, and the point I was trying to prove to you is that R1, even though it was configured to advertise the 192.168.12 network inside of RIP, okay, it would not do it until it was reachable. In other words, until R1 had a route where it could get to that network, it would not advertise it over to R2. Now R2 should be able to ping 192.168.12.1 and have no issues. And then now I can actually go here if I wanted to and do a config T int GI00 0/0. And I'm just going to put an IP add of 172.16.0.1 255.255.0.0 no shut, and then router RIP, and I'm going to do network 172.16.0.0. Now if I go back to R1 and do a do show IP route, you'll notice I now have a RIP route to the 172.16 network. But notice what happened here. Look at what I've got. I've got a route to this network, okay, which is correct. I didn't do it /24, but one of the things you will learn is in router RIP, especially version 2, you do need to put in no auto summary command so that it will not auto summarize to classful boundaries. Which in this case it didn't matter because I did /16, but if I had not, I'd actually done .255.255.0, okay. What should happen now is this should change to show IP route. It should change to /24, which it does, okay, because I put no auto summary. But if I go into router RIP and I do auto summary, what should happen is this should go back to a /16. And give it a minute. It's got to clear out the table. Clear IP route star. Yep. See how it went back to a /16? Because R2 with auto summary will auto summarize this to the classful boundary, even though what I'm wanting to advertise is this subnet, the 172.16.0 subnet. See how it actually did this. Now if I go back in here and put no auto summary, you'll see the route table change, and it takes a little while for the route table to change. Clear IP route star. I just force it to with that command. And now you'll see it's /24. So you can see the difference between it advertising the summarized classful address or classful network versus advertising the correct subnet, which is what it did. And that's what no auto summary does. But honestly, folks, I just set up RIP in what, 6 minutes, 7 minutes, And if I'd typed a little better, I could have done it in less. So very simple protocol. But the key again is I only advertise the networks I was directly attached to, and the router will only send those out if those interfaces are up and reachable, or if it is a reachable network. Okay. Same thing here. You can see we did this. We just do advertise those two networks there. Show IP protocol shows you the protocol. It shows you what versions you're sending and receiving. You'll notice here this is send receive 1, so they haven't changed over to 2 yet. They're sending version 1. Shows you the networks they're routing for. Very important, because many times your students will just put the wrong network, or they'll fat finger it. They're supposed to advertise the 1-0 network, and they put in 10-0. And I've seen that many times. Then you'll start seeing RIP routes in your table. So you can do show IP route / BN gateway, or just show IP route, either one. Now, if you want V2, this is how hard it is. Type version 2. It's literally that simple. One thing you'll learn is that version 1 is classful, which meaning that version 1 always advertises the classful mask for the networks that's on it. Version 2 will by default advertise classful mask, okay, unless you put the no auto summary command on it. And that's really there for backwards compatibility with version 1. Real world this day and age, if you're going to run, well, real world this day and age, don't run RIP, number 1. Number 2, if you happen to run RIP for some reason, run version 2, not version 1. This is where I showed you no auto summarization, turning that on. We'll also show you in show IP protocols, which I can show you again. I can actually do a show IP protocol, and you'll see that automatic network summarization is not in effect. So it actually shows you, okay? You also see this is triggered RIP, so it actually will make a change. It won't wait 30 seconds. So for instance, I'll show you a great example of this as far as triggered RIP. You know, it's supposed to be every 30 seconds it sends out its route table. So let's look here and do every 30 seconds, next one do in 21 seconds. So I'm going to do next one do in, okay, where'd that go? I lost it. There it is, 15 seconds. So we know it's getting ready to come up. What I'm going to do here is go exit. Exit, hit, should have done Control Z. So show IP route. Okay, so you see right now there's one RIP route. I'm going to go in and configure a loopback. And we talked a little bit about loopbacks. I'm going to configure a loopback with an IP address of 209.16.17.1 255.255.255.0. Okay, and I'm doing no shut even though it's already up because I'm just paranoid. You don't have to do that, but I'm paranoid. Router RIP. Okay, now what I want to do first before I put in router RIP, before I put in the command, I'm going to do a do show IP protocol. And you'll see that the next one is due in 5 seconds. So let's wait 1, 2, 3, 4, 5. Now the next one is due in 27 seconds. What I'm going to do is I'm going to put in network 209.9 was it 19? It's bad when you forget 16, 17. 209.16 209.16 17.0. Okay. Hit enter. You'll notice it's already there, even though we were probably only halfway through the update interval, because the second I added it in, it did a triggered update and sent that over, sent the entire route table over. So even though RIP is not supposed to do triggered updates, it actually does it. So don't be confused by that when you're doing your labs and you're going, well, I just put this in and it suddenly showed up. Yeah, I know. You know, it's supposed to wait, 28 seconds. Next one doing 28 seconds. But, if I do a Control A, the only thing that won't do that is if I take a network out, because of the way the route table works, It doesn't automatically, well, it did that time, it took it out. But many times if it becomes unreachable, it waits up to 30 seconds to actually put, actually more than that, it's the hold down timer, which is 3 times the update timer. So be aware that there are triggered updates inside of RIP. Now, other issues are, if you look at this particular network here, and if you were to put a snip route here, and same thing with my network, every 30 seconds, the route table is being sent out G00 on R1. Well, that is wasted bandwidth and wasted resources. So what you can do is you can define a passive interface. And in this case, you want to set the passive interface to gig 00, and then that particular interface will no longer have RIP updates going out it. It will still listen for incoming updates, but it will not go out. Now, if you do that on an interface that's actually connected to another RIP router, you're going to break your connectivity. You're going to have one-way routing or one-way updates. So remember, passive interface is only for interfaces that are not connected to any other RIP routing device. But it is a good thing to do because it does save so much bandwidth. Now, what if you wanted to propagate a default route into R1? So in other words, excuse me, into a network that's running RIP. So let's say the internet is off of R1, but I don't want to go to R2 and put a static route that points to R1 and then go to R3 and point a static route to R2. That kind of defeats the purpose of why I'm using a dynamic routing protocol. So what we can do is we can actually go to R1, the router that's connected to the internet. We can put a static default route going to our ISP. Then we can go under RIP and use the command default information originate. And it will then send a default route via RIP to R2 and R3. So we go in here and we do IP route, quad 0, outgoing interface, next hop. This is a fully qualified route. Default information originate under router RIP. And if you go and look under R2, you will actually see that you get a RIP star, which means this is a default route learned via RIP. So this is a default route that is being placed into RIP by using that default information originate command. RIP is very easy. Again, the route tables, nothing to it. Show IP route button, begin gateway. R is the command to show you RIP. Remember, this is the network you're going to. So this is for this network. The first number is the administrative distance. Second number is the hop count, because that's the metric. Where you learned it from, how long you've known about it, and the outgoing interface, the interface that you learned of it, or it's on your going to it from your router. Man, kind of tongue twisted there, didn't I? Now, the route table, the way it is set up, does have a hierarchy. And the way that these route table entries were originally set up, we're looking at classful routing. We don't use classful routing anymore. You can go in and put IP classful on a router, but that would be crazy because it would cause really weird routing behavior. So everything's classless now, but still we do have different types of routes, our directly connected routes, and that is the C and the L. And then we have our remote routes, and then we look in here on legend. Again, that's the outgoing interface, how we learned about it, destination network. Static, EIGRP, OSPF, and RIP. The good news is, in the real world, if you ever are confused, when you do a do show IP route, it tells you right across the top how you learned about it. So local, connected, static, RIP. BGP, D, remember that's because it runs dual. You'll learn about the diffusion update algorithm. DEX, which is external, OSPF, and OSPF IA. And then there's a bunch of little different OSPF versions or things that you won't learn about in this class. But those are the big ones. Remote network entries, almost exactly the same, so they do have the administrative distance in the next hop, timestamp for how long you've known about it, and then the outgoing interface. So exactly what I told you. Now, we're going to look at how the route table was set up, because it's not a flat database. It's actually a hierarchical structure. And it's designed to help speed up the lookup process. Some of this is a little bit moot because of the fact that you've got a Ceph builds that database now for very fast lookups. But it's important to know how the route table is kind of built. So first off, an ultimate route is a route that either contains a next hop or an outgoing interface. So an ultimate route has a next hop IP address on it or an outgoing interface. So all of these are ultimate routes because they're either directly connected or they have a next hop IP address. That is important because you will learn that there are different types of routes besides just an ultimate route. There are level 1 routes. Level 1 routes have a subnet mask that are equal to or less than the classical mask, which means it can be a network route. It can be a supernet route. Now, supernet, remember, has a mask that is less than the classical mask because it puts together multiple networks. And that's what this is. This is a supernet, excuse me, of all networks, 192.168 from 0 to 255, okay, or default route. Okay. Now, there are level 1 ultimate routes. In other words, those routes have a mask that are less than or equal to the classical mask and have a next hop or exit interface. So when we look in the route table here, okay, let's look for some ultimate routes. So here, obviously, is the default route. So that is a level 1 ultimate route. This is a level 1 ultimate route too because it's got a mask that is less than the classical mask, and it has an outgoing interface. So that is a level 1 ultimate route. You're also going to learn that there are level 1 routes that are called parent routes. Okay. A level 1 route that is a parent route has been networked, or excuse me, subnetted. If you go back here and look here, you can actually see one here. This is a network 209.165. This is a level 1 parent route that has been subnetted and has child routes under it. These are level 2 child routes. So when we go here, we'll see there are level 1 ultimate routes. And those are the ones that have mask, again, equal to or less than the classical mask, which classical obviously is /8, 16, and 24 for A, B, and C. And they have an exit interface or next hop address. A level 1 parent route is subnetted and has child routes under it. So when we look here in the route table, we can see these level 1 parent routes. You'll notice, are these ultimate routes? Is this level 1 route right here, 172.16.00/16, an ultimate route?
No.
No, because it does not have a next hop IP address and it does not have, it's not connected to an interface. All right. Underneath level 1 parent routes are level 2 child routes. Now those routes are going to be ultimate routes because all child routes are ultimate routes. And we'll see in the route table that 16.00 has all these child subnets under it, and 209.165.200 has all those child. So these are all level 2 child routes, and they're all ultimate routes. Now, why did this even matter? Okay, who cares, right? Well, what used to happen is this. Back in the old days, if you were doing a route table lookup, and it went through here, and it didn't match the first entry, and it went to the next entry, and it matched this part of the level 1 parent route, and it dropped into the child routes. On old, using classical routing, what used to happen is once it went into a child route, if there was not a route that matched, it would not come back out and try to find a default route. In today's world, we use classless routing. So in today's world, what happens is if you drop down into the child here, all these child routes, and let's say it was for 172.16.5.0 or 5.0/24. If it was, it would go down here and would check all these. If it didn't match, it would then come back out and look for more level 1 routes that match. If none of those matched, it would then go back to the default route. So that's why that used to matter. It's not as a big a deal anymore, especially with Ceph, because now it will jump back out and find that default route. So back up here and look again. Ultimate routes are any route, whether they're level 1 or level 2, have a next hop IP or directly connected. A level 1 ultimate route has the classical mask or less, and also has a next hop interface or connection, directly connected. A level 1 parent route is a subnetted route that does not have a next hop or directly connected interface. It does have level 2 child routes, and all level 2 child routes are actually ultimate routes because they will have an exit interface or a directly connected. Okay. Again, used to be much more important because what it would do is it would look for level 1 routes. Then if the level 1 route matched, it would go into, as I say, didn't match in the ultimate routes, it would then look for a parent route and would look through all the child routes. And if they didn't match, again, in the old days, it would just chuck it and say, well, I don't know how to get there. But in the new, with Ceph, it would actually come back out and look for the SuperNet, and if that doesn't work, then it'll go to a default route. And honestly, with Ceph, it just hits the Ceph table. Okay, that's why we used to worry about having recursive lookups. You don't need recursive lookups anymore because you don't have to worry about once it hits that ultimate route, the default route. Doesn't matter whether you're doing next hop or if you're doing outgoing interface. It's gonna sit in the Ceph table. We use outgoing interface typically because it's just easier than having to re-IP our interfaces. One of the things I will tell you is the longest match is the match that's going to match in the route table. So when you look at a destination packet, it looks in the route table at all the routes that are there, and whichever one is the longest, that is the route. The one that matches the most bits, it's going to be the one used. So IPv6, folks, is just like IPv4. Basically, you look at directly connected routes. The difference in, you see here again, route source, the prefix you're going to, the metric, administrative distance, and how it's connected. So, outgoing interface, directly connected, and then you've got the AD and the metric. Remote entry is the same thing. You see you've got remote prefix, you've got the AD, in this case this is an EIGRP route. This is the metric, this 3 million and change, and then you've got via this interface and this IP address. This tells you the next hop IP, IPv6, and the outgoing interface. Excuse me. And that is it on chapter 3. It is pretty much a simple chapter. You're going to do a couple labs on, in fact, most of you have done most of the labs on it, but real simple, easy, not a big one in terms of content. Any questions?
One real question. When I used to do RIP, so this curriculum is not going to get deep into RIP, like where we do split horizons and.
Nope.
Okay. Nope. I was preparing for that, but I'm like,
yeah, and that's one of the things that it uses this just to kind of introduce it, and then it doesn't really get into split horizon and talking about how you deal with split horizon and those types of things. The curriculum just doesn't cover that anymore.
Okay. Okay.
Good question though, because that used to be a very big part of it. So. All right. Well, next week we'll try to get through chapter 4. Let me stop the recording. Let me find the recorder.